Hello QCrypt 2020 attendees, I am Costantino Agnesi.
I'm Luca Calderaro.
We're both postdoc researchers here at the University of Padova.
And we are going to talk about our recent experiments about quantum key distribution. In particular, I will explain our latest method for synchronization in quantum key distribution.
And then I'm going to present a simple quantum key distribution experiment that exploits this temporal synchronization algorithm and also exploits the Ponyochorization Encoder. After a brief introduction, Dr. Luca Calderaro will introduce the qubit-based synchronization algorithm for quantum key distribution. Immediately after, I will introduce the self-compensating Ponyochorization Encoder. Afterwards, we will describe our simple quantum key distribution experiment that exploits the qubit-based synchronization and the self-compensating Ponyochorization Encoder. We will end this presentation with some concluding remarks. Quantum technologies promise to revolutionize our lives. For example, by exploiting quantum resources, quantum communications has the potential to solve many of the problems of classical communications, such as privacy and sequencing. Currently, quantum key distribution is the most advanced application of quantum communications. By leveraging on the principles of quantum mechanics and the characteristics of single photons, QKD allows two distant parties to distill a perfectly secret key and bound the shared information with any adversarial eavesdropper. One of the main challenges for quantum key distribution is widespread adoption in our current telecommunication networks. This has motivated several research groups to study simple protocols and to develop setups with high stability. However, in most recent QKD experiments, auxiliary tasks are performed by separate subsystems that inevitably add complexity to the QKD system. For these reasons, we are confident to state that widespread deployment of QKD on our current telecommunication networks will require the development of simple and more robust systems. With this in mind, we developed a QKD system that performs synchronization, polarization, compensation by exploiting only the hardware already needed for the quantum communication task. The synchronization is performed with a qubit-based synchronization method we call qubits for sync, which works by sending a public qubit sequence at pre-established times. Also, a predetermined qubit sequence is exploited to monitor and compensate the polarization drifts of the quantum channel. The polarization encoding is performed with the self-compensating Ponyoch scheme based on a Synchronization loop, and we implement the simplified three-state, one-decoy efficient BB84 protocol introduced in the work by Grunfelder and others.
Now I will talk about our synchronization method for QKD that we used in our experiment. Temporal synchronization is of fundamental importance for QKD. Indeed, it is needed to correlate Alice's transmitted sequence with Bob's received string. And it is also important to discriminate the noise from the quantum signal. The most adopted solutions are typically clock distribution from transmitter to the receiver via pulsed laser, or using external time reference as the one provided by the GNSS. It is also important to consider the performances of the synchronization solution because it is critical to filter out the noise. If you compare with the synchronization systems used in classical communication, you see that these systems do not require an external synchronization service. Because indeed here, the clock information is carried by the signal itself. This approach has several advantages. First, the data throughput is maximized as any physical channel is exploited for data stream. Second, you have less hardware, and this means simplicity and robustness of the system. So in the same spirit, we propose a synchronization method that we call qubit for sync, which uses the qubits exchanged during the QKD protocol to synchronize the transmitter with the receiver. In general, a synchronization method has to solve the following problems. First, it has to reconstruct the transmitter period at the receiver. And second, it has to find the time offset, which is basically the time at which the first qubit arrives at the receiver. With the qubit for sync, the main idea is to address the first point, we use the time of arrival of the qubits and perform a frequency analysis to find the transmitter frequency. The second point is addressed by performing a cross-correlation of a public qubit sequence, which is prepended to the Alice random sequence. And in doing so, we introduce a novel cross-correlation algorithm that has a computational complexity of L log L, where L is the length of the synchronization string. For what regards the period reconstruction, the algorithm has to correctly reconstruct the time separation tau of consecutive states sent by Alice in an acquisition interval t. So first we estimate the period of the transmitter, which we call tau 0a, via a fast Fourier transform of the first 10 to the 6 samples, in which the sampling rate is 4 times the nominal frequency of the transmitter. If the time acquisition is larger than the sample time, then this estimation is not sufficiently precise. So to augment the precision, we perform a linear regression of the time of arrivals in all acquisition interval, modulo tau 0a. The slope of this linear fit is then used to correct the estimation of the period. For what regards the time offset reconstruction, the higher the losses, the longer the synchronization string needs to be in order to have a significant correlation. Now, typically, since in QKD you cannot increase the power of the signal, we have to come up with a cross-correlation algorithm which is efficient in order to cope with very lossy channels. So the idea is this: assume to have a synchronization string whose autocorrelation has n1 periodic peaks. So we have n1 local maxima. Of course, there is one global maximum corresponding to lag 0. So the idea may be to find the lag or the position of any of the local maxima, and then to find the global maxima you just need to check in n1 position of the cross-correlation. Our cross-correlation algorithm can be summarized by this figure, in which we have 4 steps. In the first step, you take the synchronization string S and you rearrange it into a matrix with n1 column and L1 rows, in which L1 times n1 gives you the length of the string. You do this for both strings, the one of Alice and the one of Bob. Then in the step B, you take each row of the matrix and you perform a fast Fourier transform. What you obtain is another matrix, let's call it capital S, the one of Alice and the one of Bob. Then in the step C is the step in which we find the position of one local maxima. To do this, we take the first column of SA and the first column of SB, and we perform a cross-correlation of these two strings. The cross-correlation of these two strings has a single peak, and as I said, we can demonstrate that this peak is the position of the local maxima of the global synchronization string. Now, in the last step, we check the other n1 positions to find the global maxima, and we do this by using the other columns of the matrix. So we take the other columns of capital SA, we shift them by the U optimal, which is the position of the local maxima. We perform the internal product between each column of SA and each column of SB. And finally, we obtain a vector of n1 values. We perform the inverse fast Fourier transform of this vector, and we obtain another vector which present a single peak, and the position of single peak, let's call it J optimal, is the position of the global maxima among the local maxima. In this figure, we see the robustness of the qubit-for-sync method in terms of different conditions of the channel, like the Q-bar and the losses. In the y-axis, we have the Q-bar, while in the x-axis, we have the sifted sync bit fraction, which is the ratio between the number of sifted bits used for the cross-correlation and the length of the synchronization string. In this particular case, we use a synchronization string length of 10 to 6. The heat map here represents the simulation of probability of success of the method, while the red dots represent the successful experimental synchronization. What we see is that the synchronization can be achieved even for high Q-bar, with the lower the losses of the channel, the higher is the Q-bar with which we can still achieve the synchronization.
I will now introduce the Ponyochorization Self-Compensating Polarization Encoder for quantum key distribution. Polarization encoding has been extensively studied for quantum key distribution. Unfortunately, many of the past polarization encoders used for quantum key distribution are either expensive, unstable, or show limited polarization extinction ratios. There are even some polarization encoders that exhibit side channels that undermine the security of the implemented system. A widely used solution is the use of 4 different lasers, one for each polarization state required by the quantum key distribution protocol. This is, for example, the approach used by the Michus satellite for its quantum key distribution experiments. However, in this approach, each single laser requires its own driving electronics and a temperature controller, rendering a bulky and complex solution with high power consumption. Furthermore, any temporal and spectral mismatch between the lasers opens a side channel that can be used by a quantum eavesdropper. Lastly, as shown in the work by Lee and others, this approach is vulnerable to some quantum hacking attacks. Another popular solution is the use of inline polarization modulators. However, this approach tends to be quite unstable. In fact, these polarization modulators tend to be very prone to radiant frequency and temperature drifts. Furthermore, the required Wu-pi voltage by these polarization modulators tends to be quite high. Also, the barrier fringence of the crystal limits the achievable extinction ratio obtained with these polarization modulators. Lastly, this solution is inaccessible for quantum key distribution experiments outside the standard telecom bands because the polarization modulator needs to support both polarization modes. Yet another solution is given by the double-pass polarization modulator with a Faraday mirror, which was introduced by the work of Lucio Martinez and others. However, this approach still requires a high Wu-pi voltage and has a limited extinction ratio still given by the barrier fringence of the crystal, and also the need of a phase modulator that supports both polarization modes renders this approach inaccessible for QKD experiments outside the standard telecom bands. To solve all the previously mentioned problems, we introduced the Ponyochorization Polarization Encoder, which is constructed by placing a phase modulator with polarization-maintaining fibers inside an asymmetric Sagnac interferometer. The Ponyochorization Polarization Encoder works as follows. Laser pulses are directed to a polarization controller via a circulator. This polarization controller allows us to create a balanced superposition of the horizontal and vertical polarization modes. A PBS then separates these two modes and directs one mode in the clockwise direction while the other mode is sent in the counterclockwise direction. In the clockwise direction, a phase modulator is first encountered and afterwards we have a delay line. Instead, in the counterclockwise direction, we first encounter the delay line and only after the phase modulator. This allows us to individually address the phase of the clockwise and the counterclockwise direction, which is then translated to a modulation of the polarization state. In fact, by applying different voltages either to the clockwise or the counterclockwise direction, we can generate different polarization states, as described in the table below. Compared to other polarization modulators, the Ponyoch requires a lower Wu-pi voltage, can be developed using phase modulators that carry only a single polarization mode, exhibits no polarization mode dispersion, and has a self-compensating design that guarantees robustness against temperature and electrical drifts. The intrinsic quantum bit error rate of a source gives a quantitative and qualitative measure of its suitability for quantum key distribution. Its characterization is relevant to predict the secure key rate under different conditions, such as different channels or detector technologies. It is also meaningful to measure its stability to find how long the source can function without requiring any alignment. For this reason, here we report the intrinsic quantum bit error rate of our Ponyoch polarization encoder. Every second, the quantum bit error rate was estimated for both the key generation bases and the control bases. In 45 minutes, an average quantum bit error rate of 0.07% was measured for the key generating bases, while an average of 0.02% was measured for the control bases, meaning that we obtained an average quantum bit error rate of 0.05% for the both bases relevant for quantum key distribution. With over 33 dB of polarization extinction ratio, the intrinsic quantum bit error rate we registered here is the lowest ever reported, even considering encodings other than polarization. We will now introduce our simple quantum key distribution experiment that exploits the qubit-based synchronization algorithm and the Ponyoch polarization encoder, against which the DFB laser outputs a 50 MHz stream of phase randomized pulses with 270 picoseconds of temporal duration at 1550 nanometer wavelength. The light pulses then pass through a lithium niobate intensity modulator used to set the intensity levels required by the decoy state method. The pulses that enter the Ponyoch polarization modulator realized using only standard commercial off-the-shelf fiber components. The optical pulses then encounter an optical attenuator that weakens the light to the single photon level. A 99:1 beam splitter is used to estimate the intensity level of the pulses. The 1% output is directed to an in-gas single photon avalanche diode, while the other output port is directed to the quantum channel. In implementation, the quantum channel is formed by a 26 km spool of a G655 dispersion shifted fiber with 0.35 dB per kilometer of losses, followed by a variable optical attenuator. This variable optical attenuator allows us to introduce further channel losses in order to test the resilience of our system. The fiber receiver consists of a 90:10 fiber beam splitter, setting the detection probabilities of the measurement bases to 0.9 in the key generating bases and 0.1 in the control bases. The output arms of the beam splitter are connected to automatic polarization controllers and the polarization beam splitter. The 4 output ports are then sent to 4 superconductive nanowire single photons with efficiencies around 85%. The single photon detections are then recorded by the QTAG time-to-digital converter, which has 1 picosecond of temporal resolution and a jitter of 10 picoseconds. A computer then reads the time-to-digital data and uses it for temporal synchronization, polarization compensation, and quantum key distribution. Mechanical temperature fluctuations transform the polarization state of the photons that travel through the fiber, which in our case is the quantum channel. This transformation causes the transmitter and receiver to effectively have different polarization reference frames, inevitably increasing the quantum bit error rate. Real-time estimation of the quantum bit error rate can be fed to a minimization algorithm that acts on motorized polarization controllers at the receiver to compensate for the polarization state transformation. Here we propose a polarization compensating scheme that exploits a shared public string. In particular, ALE sends 10 to the 6 states in the key generating bases. And Bob uses this string to estimate the qubit in the key generating bases. Instead, for the control bases, Alice reveals her basis choices once each second, and Bob uses this data to estimate the qubit in the control bases. Similar schemes have already been proposed, but they require the entire post-processing of the transmitted string to work. As a result, our approach has a feedback cycle that is about 10 times faster than those approaches. Here we can see our polarization compensating scheme at work. During 6 hours, an average quantum bit error rate of 0.3% was measured for the key generating bases, while an average of 0.2% for the control bases, with the quantum channel that included the 26 nm optical fiber spool and the variable optical attenuator set to 19 dB of total losses. Here we report the security rate achieved by our QKD system at different channel losses. The losses were added by increasing the attenuation of the variable optical attenuator after the 26 km of fiber. A random qubit sequence of states was transmitted where the first L qubits from the publicly known string used for synchronization and polarization compensation. Using a synchronization length of 10 to the 6, we perform QKD runs up to 34 dB. With a length of 10 to the 7, we run QKD up to the channel loss at which the key rate drops to 0. In the QKD run with highest losses, we achieved a secure key rate of 80 bits per second at 40 dB of channel losses. Our results prove that the qubits for sync synchronization algorithm properly works even at the highest losses tolerated by the QKD. We are now ready to conclude our presentation. Here, we have demonstrated a simple quantum key distribution system with reduced hardware requirements. In fact, the same optical setup is used for 3 different tasks, that is, synchronization, polarization compensation, and quantum communication, without requiring any changes to the working parameters of the setup or any additional hardware. The Polarization Encoder we use for this experiment exhibits a record low intrinsic quantum bit error rate. Furthermore, we obtained high security rates and resilience up to 40 dB of channel losses, even with only 50 MHz repetition rate. In fact, our results are compatible with those of polarization-based systems with gigahertz-based clocks. Due to its reduced hardware requirements and the quality of the source, this work represents an important step towards technologically mature QKD systems. We thank you for the attention.